Using a table to estimate a function. Suppose we measure the velocity, v of t, in feet per second, of a bicyclist racing down a flat road every 2 seconds. How can we best estimate the total distance traveled over the 10-second interval? And how do we graph this scenario? So first we're going to talk about how we estimate it. Then we'll take a look at the picture of what we did. So we have to be careful here. Remember, if our rate was constant, we could do rate times time. However, you can see that our rates here are changing. The velocity is 0, 5, 7, 10, 15, 22. So it's not the same at every point. And we also don't know what the actual function is for velocity. So we can't even try to see if it's a rectangle or a triangle like we did before. So we need to come up with something better. The other thing we have to be careful about is what our time units actually are. So what we don't want to do is we don't want to do something like time equals 0 times rate equals 0 and time equals 2 times rate equals 5. Because if you multiply something like 10 times 22, that would mean that you were going 22 feet per second for the entire 10 seconds, which simply is not true. So what I want you to notice here on my table is that my time units are equally spaced. Between every two numbers is 2 seconds, so we're counting by twos, which means that we can break this down into small 2-second intervals. So we're going to consider what happens between time equals 0 and time equals 2. That's our first little interval here. And then we're going to look at what happens between time equals 2 and time equals 4. That's our second interval here. Then we'll look at what happens between time equals 4 and time equals 6. And then time equals 6 and time equals 8. And then finally, what's happening between time equals 8 and time equals 10. So this is what we're going to do. Because if we look at what's happening in each of these little intervals, if we can figure that out, then we can just add up all the things we figured out. Just like when we had 2 legs to our trip or 2 parts to the population growth, we were able to figure out each piece separately and just add together our answers. So that's what we're aiming for here. So I want you to notice that for each of these little intervals, they're each 2 seconds long. Okay? So that means that my time for every single interval is 2 seconds. That's really important. Now remember, if our rate was constant, we could do rate times time. Now we said that the rate was not constant. However, what we can do is we can take each 2-second interval and we can fix the rate just for that 2 seconds. But we have to do it in a way that's methodical. So what that means is if I'm considering what's happening between time equals 0 and time equals 2, my first 2-second rate, I'm going to assume that my rate was constant, and I'm going to pick that rate to be the one on the left. So there's 2 rates here. There's 0 and there's 5. I'm picking 0, the one on the left. So now when I do rate times time, I'm going to do 0 times 2. And again, that's 0 feet per second times 2 seconds. From time equals 2 to time equals 4, again, I'm going to pick the rate on the left. So rate times time is 5 times 2. Time equals 4 to time equals 6. I'm going to pick the rate on the left. Time equals 6 to time equals 8. Again, pick the rate on the left. And time equals 8 to time equals 10. Again, pick the rate on the left. So again, what I'm doing is I'm assuming that the rate is constant for each 2-second interval so that I can use the formula rate times time. Now, as I said before, each interval is only 2 seconds long, and then the rate changes, just like it did when we were doing the trip with multi-parts. But that's okay, because if we add up all these little pieces, it should give us the total distance traveled. So what we want to do is we want to add what's going on here. So if we crunch all those numbers together carefully, we're going to get 74 feet. Remember, we're doing feet per second times seconds. So when we add these all up, we get 74 feet. Now we were very methodical. We always picked the rate on the left, and then we went through our entire table to represent each time interval. However, if you are this bicyclist and you are indeed racing, right? So you want to cover as much distance as you can, you're probably going to be really angry with what we did because we didn't ever even use the 22, which was your fastest rate in all of the measurements. So it turns out that what we did is called a left-hand estimate. So 74 is a left-hand estimate. Now, you can imagine why it's called that, right? Because we always pick the rate on the left of the two rates. So there was no reason whatsoever that we couldn't have done the same thing, but used the right hand rate for each estimate. So let's go ahead and see what happens if we do that. So from time equals 0 to time equals 2, instead of picking the rate on the left, which was 0, I'm going to pick the rate on the right, which is 5. So now I'm going to do 5 times 2. My rate was 5. My time was 2 seconds because time equals 0 to time equals 2. Plus, now from 2 to 4, I picked the rate on the right, which is 7. So 7 times 2. Plus, from 4 to 6, if I pick the rate on the right, that's 10 times 2. Plus now from 6 to 8, the rate on the right is 15 times 2. Plus, now from 8 to 10, I have 22 times 2. So I multiply all these smaller pieces together, and I add them up, and I'm going to get, 118 feet. Okay? And this is called the right-hand estimate. And it's called the right-hand estimate because, again, we're always picking the rate on the right. So what does that mean? What does that tell us? What do we do with this information? So this is going to give us bounds, okay? What this means is that our total distance traveled, we'll call that TDT, total distance traveled, has to be between 74 and 118. It can't be anywhere else. Given these rates, it has to be between these two numbers, right? And these, again, are in feet. So that's useful in some ways, but these numbers are kind of far apart. If we didn't have any more information, there's also something called the best estimate. And the best estimate is the estimate that you get when you average these two things together. So remember, when you average two numbers together, you add them up and divide by 2. So when we do that, we're going to get 96 feet. Now, does that mean that I traveled exactly 96 feet? No. No, what it means is that's my best guess based on the information that I have. If I had more information, I'd be able to refine my guess to make it better. But what's really important here is this idea that we are fixing the rate to be constant for these time intervals, okay? And there's some other terminology that comes along here that's going to be really important. So I'm going to present it now in the context of this problem, and we'll define it more thoroughly later. So the first thing is delta t. So in this problem, my delta t is 2. Okay, your delta t, or sometimes delta x if you're using the variable x, is going to be the interval size that you're using or what you're counting by in terms of the independent variable. So delta t here is 2 because I'm counting by 2's, 0, 2, 4, 6, 8, 10. The other important variable here that we're going to start talking about is n. N is the number of estimates that I'm making. So here, I had 1, 2, 3, 4, 5. So here my n equals 5 because I used 5 distinct time intervals to approximate what was happening. Now, you may not have put this all together yet, but we're going to see each of these time intervals represents a rectangle. So when we graph this to look at this situation, we'll be able to see that we used 5 rectangles to approximate the area under the quote unquote curve to approximate the total distance traveled. So let's look at a picture of this and see if we can visualize what's going on in this scenario. So our picture here is a graph of your velocity versus your time. So remember, all of our times were in 2-second intervals. So you can see here that we're determining what's happening between 0 and 2, 2 and 4, 4 and 6, 6 and 8, and 8 and 10. When we do a left-hand estimate, for the first 2 seconds, we assumed that the rate was 0 because that was the rate on the left. So if you look at what's happening in the orange, you can see that we have a line at velocity equals 0 from 0 to 2. And then from 2 to 4, the rate we assumed was 5. So we have this constant line at 5. From 4 to 6, we assumed the rate was 7. That's a 7 there. That one we said was a 5. We assumed this rate was 10. And we assumed this rate was 15. So you can see that we're constant for each 2-second interval. And then in order to get the area of each block, we are doing our rate, which is the height of the block, times our time, which is 2 seconds for each, or the width of the block. So if we do 2, which is the width, times 15, which is the height, right? That's our y value. We get 30. We have 2 times 10, which is 20. 2 times 7, which is 14. And 2 times 5, which was 10. We'd also have 2 times 0, but that's 0. And it was adding those numbers together that gave us the 74. So this is, again, a left-hand estimate. That's what we're doing. We're turning each time interval into a rectangle. So we do the same thing with the right-hand estimate, right? So now for each interval, we're assuming the rate on the right. So that's 5. And then this one goes up to 7. And then this one goes up to 10. This one to 15. And this one to 22. So the area of this whole block is 22 times 2. Because again, the width is 2. That's 44. This is 15 times 2, which is 30. Again, this whole block, it crosses over. 10 times 2, which is 20. Right, this one's 14. This one is 10. So we can see that these areas are represented the same way we were graphing them before. Only now we're turning each of our little intervals into these constant rates so that we can use rectangles, because rectangles are something we know how to get the area of. Now, something even more interesting happens when we're graphing a scenario like this. If we connect the points of the left-hand approximations, right, we get something that looks like this, which is the same thing we get if we connect the corners of the right-hand approximations. So what I want you to notice here is that my orange rectangles, right, if we're approximating the area under the curve, the left-hand estimate is an underestimate, right? Because it doesn't quite capture all of the areas. It's missing all of these areas under the curve if we were trying to get the exact estimate. The right-hand estimate in this scenario is an overestimate because look at all the extra area above the curve over what the actual area is, right? So when we find a left and a right-hand estimate, one of them is an overestimate and one of them is the underestimate. The overestimate is going to be whatever the bigger number is, and the underestimate will be whatever the smaller number is. So that's why we have that interval of 74 to 118. One of them is too much area, the 118, and one of them was not enough area, which was the 74. It has to be somewhere in between. But we get a general sense of what our graph looks like by connecting those points from the left and the right hand estimates. And again, with the left hand estimates, the red rectangles, you can see that the left hand corner of every rectangle touches our function. But with a right hand approximation, it's the right hand corner that always touches our function. So we can predict that our function looks roughly like this because we're able to connect those corners. So let's circle back to the different terms we've learned and the vocabulary we've been using to talk about these estimates.